So if you remember, like from edge detection algorithms, what we were trying to do is at any given location or any pixel location, we were looking at the neighboring pixels, right, in the direction of the orientation. And if the magnitude of this edge being detected is greater than the neighbors, we say that this is an edge. But if it's not greater than these two, we say this is not an edge. So it's kind of you're suppressing if it's not like dominant in the neighborhood. Okay, so that's the name like non-maximum suppression. If it's non-maximum, we suppress it. So the idea remains the same, but what we do here is it's like slightly modified algorithm. So whatever detections you have for any given image, it will be a long list, right? Because you might have multiple objects present. Now what you do is you first of all sort like all the detections based on the confidence score. Okay, so what you do is you go to the bounding box, which is like your model is actually very confident. It's saying like 100% this is a person. You start with that. Now what you do is you take that bounding box and compute the overlap of that bounding box with all the other detections. Okay, and the kind of overlap you will compute, it's called intersection over union. And again, this is a very important term. I think you're using for NMS, that's fine. But I think if you're solving detection problem, like whether you do evaluation, whether you like do some kind of loss computation, you will see like different variations of this intersection of over union. So try to understand like what this does. So first of all, you have two different detections. Okay, so there are two parts, numerator and denominator. So in the numerator, as the name says, intersection over union, right? So in the numerator, you will have intersection, and in the denominator, you have union. So intersection means what part of these two bounding boxes is common. And in this case, you can see like this blue region over here. That's the common part, right? So we just found, we find this area, whatever this area is, we put that in the numerator. And union is, we just combine like both the detections. And we just find like the area of this overlap, or not overlap, just like the union of these two bounding boxes, this blue color over here. And we put that in the denominator. So this intersection over union will tell you like what's the overlap between two different bounding boxes. Okay, so you do that for all the bounding boxes you have. You start with the highest one, and then what you do is if you find like there is like a high overlap between two different bounding boxes, you will keep like the highest scoring bounding boxes, but all the others you will just get rid of them. You will just remove them. You say that it's not detection anymore. Okay, now one trick here. So the trick is it's saying like high overlap. Now the question is, how do you define high overlap? And that's kind of arguable, and it will change a lot, like your performance a lot. And so again, this is like you can say a parameter. And even when we try to evaluate these object detection algorithms, later we will see we make use of this threshold as like one parameter. So we try to compute the performance of the algorithm at different thresholds. Okay, so this part is actually important. We will revisit this later. But for now, you can say that, okay, we have some kind of threshold. If IOU is, so this is going to be like between 0 and 1, right? So the best score you can get is 1, which means that it's a perfect overlap, because what will happen is your intersection will be the area of the square, and your union is also going to be the intersection of that square, because it's perfectly overlap. They are on top of each other. Okay, so the maximum score is 1, the minimum is 0 when there is no overlap at all. So union will be a big number, numerator will have completely 0. So then you can set a threshold, let's say 0.5, and say that, okay, if it's greater than 0.5, it's an overlap. If it's less than 0.5, you will keep both of the bounding boxes. Okay, so usually it's 0.5. Now let's try to understand with a simple example over here. Now this blue bounding box over here, let's say that was the bounding box which your model was saying with the highest probability this is a person. So we start with that, and we compute the intersection over union of this bounding box with all the other bounding boxes. And clearly, visually, you can, if you inspect this, you can see that all these bounding boxes on the right, literally there is no overlap at all. So you will still keep those. But now if you look at these bounding boxes, which are in the neighborhood, so some of these will have to go away. And again, that will depend on whether the intersection over union is greater than 0.5 or not. If it's greater than 0.5, you will just remove those. If it's not, you will keep those. And it may happen that if two individuals are standing next to each other, you might have like some kind of overlap between detections of those two bounding boxes, right? So in that case, we need this threshold. So one thing which you should understand here is this number 0.5 has nothing to do with like, although it's giving you like what's the overlap, but it doesn't mean that it's kind of 50% overlap, right? If it's 0.5, or if it's 0.75, it doesn't mean like the exact overlap is 3 by 4th. We will come to that, like how this number varies. Okay, so let's say this is the second bounding box with the highest second highest probability, and of course, so this we keep. So we just get rid of this. We don't use this for like future IUS scores, because the IUS scores are not going to change, right? So we just save the computation cost. Again, for this blue box, we'll compute intersection over union with the rest of the bounding boxes. And again, we will get rid of the ones which are clearing this threshold. And you can see that some of these bounding boxes are actually overlapping, but the threshold might not be that high. So we still keep those. And you do that, keep doing that for all the bounding boxes. And finally, we get a result like this. So this is much cleaner. Okay, so that was the post-processing step. And you can see like already like this algorithm is doing pretty well. And then next, I think we'll see how we can evaluate like this kind of algorithm.